cause is what happens after magma is formed. But before we proceed with our topic, let us know first what is magma and what happens before magma is formed. According to Wikipedia, magma from ancient Greek magma, meaning thick unguent, is the molten or semi-molten natural material from which all igneous rocks are formed. Magma is found beneath the surface of the earth. Besides molten rock, magma may also contain suspended crystals and gas bubbles. Magma is produced by melting of the metal of the crust in various tectonic settings, which on Earth include subduction zones, continental reef zones, mid-ocean ridges, and hotspots. So what happens before magma is formed? So magma forms from partial melting of mantle rocks. As the rocks have moved upward or have water added to them, they start to melt a little bit. These little blobs of melt migrate upward and coalesce into larger volumes that continue to move upward. They may collect in a magma chamber or they may just come straight up. At the end of this video, we can describe what happens after magma is formed. Here we can see the different types of magma and their solidified form. We can see here their chemical composition, temperature, viscosity, and gas content. And as a little recap, these three affects the formation of magma, and each type of magma has different gas content, temperature, viscosity. And here we can see that the rhyolitic magma has the higher viscosity and gas content. We also discussed the processes for magma generation and where it is generated. Increase in temperature occurs in hotspots, while the decrease in temperature occurs in spreading margins, while the addition of volatiles happens at subduction zones. So what happens to magma after it is formed? So let us imagine we have a glass container and we have a rock and a styrofoam. You decided to throw the rock and the styrofoam in the container. You can see the rock stays at the bottom and the styrofoam floats. It's because the styrofoam is less denser than the rock. This is the same with magma because of the density contrast. Magma is less dense than the surrounding country rock. Magma rises faster when the difference in density between the magma and the surrounding rock is greater. So let us remember that at deeper levels, magma passes through mineral grain boundaries and cracks in the surrounding rock. When enough mass and buoyancy is attained, buoyancy is the power to float, the overlying surrounding rock is pushed aside as the magma rises. Depending on surrounding pressure and other factors, the magma can be ejected to the Earth's surface or rise at shallower levels underneath. This figure shows two processes as magma rises. First is the ejection, where they are ejected out to the surface through volcanoes. The second one is the solidification within shallower levels, so they form intrusive igneous rock.
I do not. I've heard of it though.
At shallow levels, magma may no longer rise because its density is almost the same as that of the country rock. So the magma starts to accumulate and slowly solidifies so it will not go out.
Now another factor that affects is the viscosity. So viscosity is the measure of a fluid's resistance to flow. Magmas with low viscosity flow more easily than those with high viscosity. Temperature, silica content, and controlled viscosity of magma. This table shows the relationship between these factors and the viscosity. Okay, now mafic magma is less viscous than silicic magma because it is hotter and contains less silica. So as you can see, The higher the temperature, the lower viscosity it is, and since it contains less silica, the viscosity also decreases. So remember, temperature and viscosity inverse relationship, silica content and viscosity have direct relationship. Okay. Also, the volatiles in magma decreases viscosity. So when there are more volatile substances in a magma, the viscosity decreases.
Okay.
Some of you may recognize this figure or diagram. This diagram is called the Bowen's reaction series. So, Norman L. Bowen explained why certain minerals tend to occur together while the other minerals are almost never associated with one another. In the early 90s, he heated powdered rock material until it melted. He allowed the molten material to cool down and observed the mineral that formed in the rocks. He repeated this process with progressively lower temperature, and the other result he got led him to the now called Bowen reaction series. Up to this day, this series is still accepted as the idealized progression of minerals produced by cooling magma. The quotation, pressure, and temperature where rocks are formed can be inferred from this.
I don't understand. I don't understand, bitch. I don't understand. I don't understand, bitch.
This series shows how certain minerals are stable at higher melting temperature and crystallize before those stable at lower temperature. This series also explains how minerals are formed under different temperature conditions, giving that all the required elements for earth minerals are present.
Now let's talk about the discontinuous branch. The discontinuous branch describes how ferromagnesian minerals in the magma are transformed as the temperature changes. So ferromagnesian minerals are silicate minerals. It is a collective term used to cover such minerals as the olivines, pyroxenes, biotite, and many others. The early formed crystals, olivine in this case, reacts with the remaining melt as the magma cools down and recrystallizes into pyroxene. So here we can see olivine and this is pyroxene. Further cooling will transform pyroxene into amphiboly. If all iron and magnesium in the melt is used up before all the pyroxene recrystallizes to amphiboly, then the ferromagnesian minerals in the solid rock would be amphiboly and pyroxene and would not contain olivine or biotite. So as you can see here, iron and magnesium here plays an important role.
So what are the important things or concepts